Hello everyone, welcome to Mechanical Design. In today's lecture we are going to continue our discussion of Mohr's circle, learning how to actually draw the diagram and what the diagram means, and then we're going to do an example of solving for the principal stresses and directions and elements, the extreme valued shear stresses, directions, and elements, and then finally drawing a Mohr circle example, right, of a real problem. So let's go ahead and begin this lecture with the equations for our principal stresses and directions. Let's remind ourselves of these equations because they're very key to then being able to draw a Mohr circle. So let's remember that there exists principal directions at which our normal stress is maximized, right? And we can find those using the following equation. Tan of 2 phi p is equal to 2 tau xy divided by sigma x minus sigma y, right? From this equation, we produce two angles, a phi p1 and a phi p2. And we also can find that there exists a relationship between these, between phi p1 and phi p2, where phi p2 is equal to phi p1 plus or minus 90 degrees. Now when we take these two angles, once we've found them, when we take them and plug them back into the normal stress and shear stress equations, right, those forms for an arbitrary angled cut of a 2D element, we're able to find the values of our principal stress. And we'll find those values of principal sigma 1 and sigma 2 being equal to sigma x plus sigma y divided by 2 plus or minus the square root sigma x minus sigma y divided by 2 squared plus tau xy squared. Let's extend this square root a little bit here, right? And where sigma 1 is larger than sigma 2. It's greater than sigma 2. And also where tau, let's turn this feature off here, where tau is equal to 0. So we pretty much have the equations we need here for principal stress. And then we can repeat this process and find the equations for extreme valued shear. So for our extreme valued shear stress. And let's move this figure down and let's build the equations for extreme valued shear. So let's start with the angles. What are the directions for extreme valued shear? Well, the equation we would produce is tan 2 phi s, where phi s are our directions, is equal to negative sigma x minus sigma y divided by 2 tau xy, where when we evaluate this equation, we find both a phi s1 and a phi s2, and the relationship between these two is that phi s2 is equal to phi s1 plus or minus 90 degrees. When we plug these equations, when we plug these angles back into our normal and shear stress equations for a element that's been cut at an arbitrary angle, we'll find the following. We'll find that normal stress exists and is equal to an average stress, sigma x plus sigma y divided by 2. And our shear stress exists as two different values. So two extreme values, 1 and 2, which are equal to plus or minus the square root sigma x minus sigma y divided by 2 squared plus tau xy squared. And now let's circle all our key equations here. And let's move this one down a little bit. And so we can actually see that we have both the directions, which are the angles, as well as the magnitude of the extreme value shear stresses and the principal stresses through these series of equations. Now the question becomes, how do we plot these points of interest, the principal stresses as well as the extreme value shear stresses, as functions, or plot them on an axis of normal stress and shear stress? How do we actually see where those lie when the x-axis is normal stress and our y-axis is our shear stress? Well, we do that by creating Mohr's circle. Creating a Mohr circle diagram. And let's write Mohr's circle here. And let's rearrange this here. Change our setup a little bit. Mohr's circle. And let's look at Mohr's circle and try to dissect it, because there's a lot of things that are going on in this initial drawing we have. So this diagram that you see on the screen is Mohr's circle. And there are a lot of things going on. So first we're going to introduce it fully described, and then we're going to go step by step and illustrate how do you actually build out this diagram. So let's start with drawing our axes of interest. Our x-axis is normal stress. And our y-axis is shear stress. I don't know why that happened. Let's try draw one here. And then let's move it over. Our y-axis is the shear stress. And so it can be any value of normal stress on the x-axis and any value of shear stress on the y-axis. So sigma and tau. And we consider positive normal stress is towards the right. And we consider positive shear stresses to be below the x-axis. So if you remember from our previous video, we talked about what is considered a positive shear, what's considered a negative shear, and where they would be plotted with on the axes, right? So we've kind of defined those lines, and our point O here is where we have no stress. So at that point where these lines intersect If we were to choose that point, there's no normal stress and no shear stresses on our element, right? Now, Mohr's circle is a circle. It's not the oval shape that we have here. Maybe let's make this a little taller so it looks more spherical. Okay. Mohr's circle is a circle that represents all the possible combinations of stress that could exist in an element. So if we were to cut that element at different values of phi, and let's turn the feature off. If we were to cut the element at different values of phi at different angles, each point on Mohr's circle represents a different angle, right? A different actual angle of cut, and each point has a combined value of normal stress and shear stress. So there's some, normal value here, and there's some shear value here that is associated with a particular angle. And so as we move along this circle, we're going to actually be finding combinations of normal and shear stress that are at different angles of cutting our 2D element. Now, why is that important, or why is that interesting? And let's actually leave that little example one there. Why is that important? Well, it's important because we can then define where our principal stresses are going to happen, and then we can also define where our extreme value shears will happen on this circle. We can actually find those points of interest. Now, let's remember. Let's go up and let's remember. With principal stresses, when we look at the values of stress we get, we find two normal stresses, sigma 1 and a sigma 2. And we know that when we have our principal stresses, that the shear stress is equal to 0. So, if that's true, if that we have normal values, shear stresses are equal to 0, and sigma 1 is greater than sigma 2, then we go down to Mohr's circle. If we look, we say our shear values is equal to 0. So we are going to be on the x-axis, and our larger value will have the position sigma 1 and 0, right? Because there's no shear. And our smaller value will have the position sigma 2 and 0 because there is no shear, right? So we've actually been able to define two key points of interest where our principal stresses are with respect to our body. Similar to that, let's look at our stream valued shear stresses. When we are at those angles, we find that we have a normal stress, and that normal stress is just a single value, and it's equal to the average stress, average normal stress, so sigma x plus sigma y divided by 2, right? And with that normal stress, there's also two values of shear stress, of extreme valued shear. This is tau 1 and tau 2. So if these tau 1 and tau 2 have the same normal stress, then when we go down and we look at a little diagram here, we're going to find that if they have the same value and equal, if they have the same value of normal stress and equal and opposite values of shear stress, meaning the plus minus term in tau 1 and tau 2, then we can define that we have our average stress at this point, we have our average stress at this point, and then we have a tau 1 and a tau 2, which represent the different values of shear stress between our 2 points, right? So tau 1 and tau 2, right? So now we've actually found several points of interest on this Mohr circle. We found where the first principle and second principle act. We found where our first extreme value and our second extreme value act. And we're actually able to form this circle with those points of interest. Now, another line that we need to draw and that we need to consider is the line that represents the angle that the standard or the original state of stress takes through our circle, right? Because we have sigma x, a sigma y, a tau xy. We have this stress element. Where does that lie? At what point or position around this body does that lie? Well, we'll draw a line to represent where our stress, our original state of stress, passes through Mohr's circle. And the positioning of this line is very dependent on the shear stress. If this line is going to be above or below the shear stress, above or below the x-axis of this diagram, is very much dependent on the shear stress. So if we have positive shear stress, such that it creates this counterclockwise sense of rotation, then we are going to define our axes, our positive x-axis, as below the sigma line, the sigma x, right? We'll define it as below, where the right hand end here is the positive x-axis in our original coordinate system, and this end over here is the positive y, right? And we can find, if we understand that this line represents our original coordinate system, if we understand that, then we can actually find that if we go from our original coordinate system and we cut by 2 phi p, we can find our principal stresses, our principal stress orientation, right? Remembering that every point around this circle is associated with the value of phi. Well, if we have this line of x and y, of the x and y axes, then we can say, hey, from the positive x to the positive sigma, the angle is 2 phi p, right? So we can actually graphically figure out for different values of phi where we should, where we will exist in this body, right? And that's pretty much how we, or that pretty much defines most of the key points of Mohr's circle. Now, there's 2 equations that we can introduce to very quickly draw Mohr's circle without going point by point and analyzing each point. And that is an equation that describes where is the center of Mohr's circle. And that is simply the average stress, so sigma x plus sigma y divided by 2, and 0. Because our Mohr circle always, the center of that is always going through that zero, has 0 shear, right? And then we can also define the radius of Mohr's circle. The radius is equal to square root sigma x minus sigma y divided by 2 squared plus tau x y squared. So you can see that we're reusing these same terms that we've seen previously, right? So these two actually make it a much more efficient for us to find our Mohr's circle here. So now that we've kind of identified these key points of interest, let's go ahead and work step by step to build up a Mohr's circle. So how do we draw this Mohr's circle? Okay, so we have two choices. We can start directly with finding the center of our circle and then finding its radius and drawing the circle. Or we can start with locating the values of our principal stresses. So exercising our equations and finding principal stresses. What I like to do is I like to start with plotting the principal stresses. So finding them using our equation and plotting their locations. Because I know that for principal stresses, the shear is equal to 0. So I draw my coordinate system, normal, shear, we consider to the right is positive and downward is positive, right? I apply my equations for principal stress, and I find my principal stress 1, and I find my principal stress 2, the locations of those 2 points of interest. Once I've found those points, the next step that I do is I plot the center of my circle, remembering that the center is located at sigma average and 0. And once I have that average stress, I can very easily determine the locations of my extreme value shear. Right? So with these 5 points of interest, I can then very easily draw a circle that represents Mohr's circle, the path that this that normal and shear stress takes at different angles of cut. Now our last step is then to draw a line that indicates our original state of stress. So the state of stress that we start with, sigma x, sigma y, and tau xy, drawing a line that represents those. And remembering that a positive shear stress is going to be plotted below below this line here, positive shear stress. So if we have a positive tau xy, we're going to plot below, and then we need to find the values of where sigma x and sigma y lie in this diagram. And when we do that, we can actually find a line, and that line could be, but isn't always, this is something that's very key, that these point of interests we actually have to evaluate based on their magnitude to find, is sigma x here or is sigma x there? Where is that sigma x? But in this case, sigma x here, tau xy, and sigma y here, tau xy, right? So now that we've got all of these point of interests defined, so we've got our sigma, our normal stresses, our extreme value shear, and we also have the line that represents our original state of stress, we can then figure out the angle that exists between the x-axis and our principal direction as being the angle 2 times phi p, right? And we can say that that angle can be found as tan 2 phi p is equal to 2 times tau xy my pen is freezing on me a little bit here. 2 tau xy divided by sigma x minus sigma y. So this is pretty much the procedure that we're going to follow when we're trying to draw a Mohr circle. And there's variations. You may choose to want to directly find the center, plot the radius, and then draw a line that represents those points of interest, and then very quickly find these other 4 points. But it's completely up to you. At the end of the day, no matter what approach you take to finding Mohr circle, the circle that you find in the end is going to be identical. So the Mohr circle that we've just looked at represents the Mohr circle for a 2D element, right? So what happens when we actually move to a 3-dimensional state of stress, where we have a 3D element, right? When we go back to a 3D element, well, what would our Mohr circle look like? Well, it actually looks a bit more complicated, because in 3 dimensions, we are actually going to have 3 values of principal stress. And in 3 dimensions, we're also going to have an additional value of extreme value shear, right? So let's consider, let's first consider two dimensions. Let's say that we take a 3-dimensional element, we slice it and look at only a 2D sliver of it. Well, we'll end up with, and so say we just look at the x-axis and the y-axis. So we look at that sliver. We'll build a Mohr circle for those 2 directions, for the x and y-axis. If we repeat that for another pair of axes, then we'll find another Mohr circle for the second pair. So maybe x and z or y and z, right? And then when we evaluate our third pair, we're actually going to find another circle. And that circle encompasses the extreme ranges, the true extreme values of the shear stress, right? So when we're looking at our 2D problem and we find our shear stress, we call those shear stresses extreme value stresses, right? Extreme values, because technically they don't necessarily represent the maximum shear stress that exists in our 3D geometry, right? So our maximum shear stress is actually something that we may have not found when we're dealing with our 2D problems. And so when we want to find our principal stresses, we have a much more complicated equation to do that. And to find our extreme values of shear in 3 dimensions, we have this relationship. And our maximum shear stress is actually going to be the difference between the first principal and third principal divided by 2. So it's going to represent that actual outer Mohr's circle that encompasses all of the stress within our body. So when we're dealing with 3D problems, Mohr's circle is very challenging. There are 3 circles that we actually need to generate here to really understand behavior. Luckily, in this class, we are mostly going to focus on 2D elements, and yet 2D elements by themselves still are very challenging. And there's a lot of equations that we've got to work with in order to try to solve these problems. So let's go ahead and try to do an example of doing Mohr's circle so that we can get a little more flavor for it with real numbers, and from there figure out how to draw our Mohr circle. So let's do an example from the book, example 3.4. And in this example, we are given plane stress. We are given the state of plane stress where sigma x is equal to 80 megapascal, sigma y is equal to 0 megapascal, and our tau xy is equal to 50 megapascal clockwise. And let's move this down, and let's clean this up so we can look at it a little bit better here. So the tau xy is 50 megapascal clockwise. Now, what is that 50 megapascal? What does the clockwise indicate to us? Well, if we draw our stress element, and we can go ahead and draw our normal stresses on here. So we've got our sigma x here. It's positive, so we've got tension, right? So and our sigma y is 0, so we have nothing there. Let's go ahead and draw the shear stress tau xy. So the 50 megapascal clockwise means that if we look at the positive x line, so the line on the positive x, and the positive x, or normal to the positive x, right? And we draw a shear value. Well, that shear value is something that's going to cause a clockwise sense of rotation of this body. And building from that, we can then build what our element will look like, what sense our element will have, right? And if we remember from our previous lecture, if we have, with just that positive x side, a clockwise sense of rotation, then when we build the values of shears that are needed, we are actually going to skew counterclockwise. We're going to have a counterclockwise skew. So what that actually means for us, all of this really means is that tau xy, when we use it, is going to be equal to negative 50 megapascal, because this is a negative shear stress that we have here, right? That's actually what we're dealing with. So the knowledge clockwise tells us how to draw our stress element, and then also how to use our shear stress in our equation. So now that we've done that, let's go ahead and hear what the first part of this problem is. So part A of this problem is to find the principal stresses, directions, and the stress element. So what does the element look like with those principal stresses? It's 1, 2, three things that we need to do for part A of this problem. So let's start doing that. Let's start solving this problem. Now, we can always go directly and solve the principal stresses. We have an equation for that. But a better option, the option that I always like to do, is first solve for the directions and use the directions to tell me which stress is sigma 1 and which stress is sigma 2, right? So actually going step by step, taking the directions, plugging them into the normal stress equation, finding which principal stress that I found, repeating that, and then being able to associate sigma 1 with phi 1 and sigma 2 with phi 2. So let's try that. Let's start with finding the principal directions, which is tan 2 phi p is equal to 2 tau xy divided by sigma x minus sigma y. Okay, we look at this equation, we have everything on the right hand side and we're searching for phi p on the left hand side. So let's rearrange and solve for phi p. If we do that, we'll find that phi p is equal to half of tan inverse 2 times, and let's put the numbers in there, 50 megapascal divided by 80 megapascal. And note that we're putting that negative sign, the negative shear sign, in there, right? And when we solve this equation, plugging everything into our calculator, we'll find we have two angles. We have negative 25.7 degrees and we have 64.3 degrees. We have two angles. And the problem is we're not sure which one is phi p1 and which one is phi p2. We don't know. There's nothing that exists that tells us which one is which. And so what we need to do is we need to take these angles and plug them into our normal stress equation and determine which one is sigma 1 and which one is sigma 2. So let's grab our normal stress equation. And that equation is that normal stress is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 phi plus tau xy sine of 2 phi. Right? That's that general equation we had for any angle of phi. Well, let's go ahead and plug in the two phi p's that we found, and from that we can determine which is which. So let's plug in phi p equal to negative 25.7 degrees. So let's replace the phi with phi p, right? All right, let's do that. Our sigma is equal to 80 megapascal divided by 2 plus 80 megapascal divided by 2 cosine 2 times negative 25.7 degrees plus negative 50 megapascal sine 2 times negative 25.7 degrees, right? So we go ahead and plug in the things we know, and plugging in that first phi p, the one we're not sure if it's phi p1 or 2 or whatever, we plug it in, put it in our calculator, and we'll find that the normal stress is 104.03 megapascal. All right. Now let's repeat this process. Let's repeat it for the other phi p. The other phi p is 64.3 degrees. We plug that into our normal stress equation. First term is the same. Second term times cosine of 2 times 64.3 degrees plus that times sine of 2 times 64.3 degrees. We plug all that stuff into our calculator and we will find that the normal stress with this angle is equal to negative 24.03 megapascal. So now we've got our two principal stress values. And then what do we need to remember? We need to remember that sigma 1 is greater than sigma 2, right? Got to remember this relationship. So if sigma 1 is greater than sigma 2, we can figure out which of these two normal stresses is sigma 1, and then subsequently which ones which one is phi p1 and phi p2. So, let's just do that. Let's go ahead and note that sigma 1 is the larger value, 104.03 megapascal, and that's at an angle phi p equal to negative 25.7 degrees. Right? And then sigma 2 is equal to negative 24.03 megapascals, and that is at an angle of 64.3 degrees. And so taking this approach, we're able to find the directions, and from those directions define which one is sigma 1 and sigma 2. Now you may be tempted to directly find sigma 1 and sigma 2. Right? You may be tempted to just use the equations we have for sigma 1, sigma 2. Right? And you would be able to find those, and it would tell you which one is sigma 1 and sigma 2. But the problem is that you wouldn't then be able to take those numbers and associate them with the correct angles. So it's always good to start with the angles, as we did in this problem, find them, and then plug those angles into the normal stress equation and find different values of normal stress. And then from there you can figure out what order or which normal stress is sigma 1 and sigma 2. It's very important for you to be careful and at that step. And if you forget, then when you're doing an exam or you're doing a homework problem, you can get stuck and not be able to fully complete the problem. So this problem wanted us to find the principal stresses, their directions, as well as we were asked to draw a stress element. So let's go ahead and take our original stress element here. Let's copy that, which is our original stress element. Oh, let's see. I got to turn off the objects. Okay. Original element. We need to draw a new element, which is our principal stress element. And this element is, in essence, the idea of rotating the original element. So if we were to rotate the coordinate system of this original element in order to have an element where only our principal stresses are acting, right? So, in fact, let's start over. Let's recreate our original element using our shapes feature, so we can have a nice, beautiful little element here. Got our original element, got a coordinate system, and let's draw the element. Okay. And let's define our axes. A positive x-axis, a positive y-axis. And then let's draw our original state of stress. We have a sigma x here, which is 80 megapascal. It's positive, it's causing tension, right? Our sigma y was equal to 0. And then our shear stress is equal to 50 megapascal clockwise. So let's take our positive x line and let's draw an arrow that would cause a clockwise sense of rotation, right? And then let's build up the shear terms that are needed to maintain equilibrium across these other surfaces. And write that as 50 megapascal, where it's known that the values of these shears are all equal but have different directions, right? So that's building our original element with its original plus x and plus y coordinate system. Now let's create our principal stress element, which is a rotated element that's rotated at the angles, principal angles, to produce just normal stresses, to produce just our principal stresses. So let's erase these things here, and let's delete that. And let's draw a line from let's draw a line. Oh, here we go. Okay. And the line represents the distance from our plus x-axis, our positive x-axis, to the orientation where our principal stresses reside, right? Now we've got two orientations, two angles. We have a VP1 and a VP2. And those are the distances from the positive x-axis. Let's start with VP1. So the VP1 from the positive x-axis, let's go and draw that. Since it's negative 25.7, we are going to be going clockwise here to indicate that negative value, clockwise from the positive x-axis, right? And then we can also draw, oh, let's go blue, another line for our other angle, and again starting from a positive x-axis, but this time we're going up, which is a value of 64.3 degrees. Now when we take the value of these two angles, we'll find that the lines they form is are right to each other, or orthogonal to each other, right? So we've actually defined the directions where the principal stresses are going to act. So let's draw our element now. And of course, I'm not a perfect artist here, but let's do this like that so it looks more right. And let's also make that touch a little bit more here, right? So now we've actually drawn the element. We did all of that. Now we have the element that we want. And now we need to put the values of the principal stress onto this body. So we have our VP1 here from the positive x to the direction where sigma 1 acts. And our sigma 1 is equal to 104.03 megapascal. And for equilibrium, should be applied on the other side of the element, right? And then our line here, which is from the positive x-axis up 64.3 degrees, well, that's associated with our sigma 2, which is 24.3 megapascal. Of course, it's negative, so we're putting this element in compression. And to maintain equilibrium, on the other side, we're going to also be going inwards. And so we created our principal stress element that describes what orientation our specimen would need to take to have only principal stresses acting on it, right? Okay, so we've completed part A. We found the principal stresses, their directions, and we were also able to draw our principal stress element just using the properties that we know about the directions and the values themselves. So let's continue with this problem because there's another piece to it. For part B, we need to find the extreme values of shear stress, their directions, and the stress element, the extreme valued shear stress element. And let's save here, and then let's edit. Shear stress. There we go. So now we've got to do the same problem, but now we're searching for the extreme values of shear. Well, let's use the same procedure. Let's do it step by step. And let's start with tan 2 phi s being equal to negative sigma x minus sigma y divided by 2 tau xy. Right? The equation for finding the directions. If we look on the right-hand side, we know everything. And the left-hand side, the only thing we don't know is phi s. So let's rearrange and find phi s being equal to 1 over 2 tan inverse. And let's go ahead and plug our numbers in here. So negative 80 megapascal divided by 2 times negative 50 megapascal, right? When we plug this into our calculator, we'll find 19.3 degrees and 109.3 degrees. And when we look at it, we're not really sure which one is phi s1 or phi s2. So let's go ahead and plug these equations in and see what we would get. Well, not equations, but the angles in and see what we get. So let's start with phi s equaling 19.3 degrees. And let's plug that into our stress, normal stress and shear stress equations. So, I'm going to assume that we shall have these equations. So it would be 80 over 2 plus 80 over 2 cosine 2 times 19.3 degrees plus negative 50 sine of 2 times 19.3 degrees. And then our tan equation is negative 80 over 2 sine of 2 times 19.3 degrees plus negative 50 cosine 2 times 19.3 degrees. So we're just plugging them into those general equations, and we'll find that sigma is equal to 40 megapascal, and our tau here is equal to negative 64 megapascal. All right, and we can repeat this for our other angle, is sigma s equaling to 109.3 degrees, and we will find that sigma is equal to 40 megapascal, and tau is equal to 64 megapascal. So now we've kind of defined, remember, and of course we know that our extreme values are going to be plus or minus each other. But now we've enforced that, hey, for both of these cases, the normal stress is equal. And for both of these cases, the magnitude is the same, but the sense is opposite. So let's go ahead and draw these all out here. Or let's draw out what we found, that sigma is equal to 40 megapascal. One of the taus is negative 64 megapascal, and that is at an angle equal to 19.3. The other tau is 64 megapascal, and that is at an angle of 109.3, right? So let's go ahead and box this in. These are the values that we need to know. And so now we have both the values of our extreme values of shear, their directions, as well as the normal source, the normal stress that is associated with each of those values. So now let's go ahead and build our element. Let's build our, let me change the font size here. Our extreme value shear stress element. So let's go ahead and start with the coordinate systems. Right? This probably doesn't need to be that long. Shorten it a little bit. With positive x here and positive y here, right? And then let's start with one of these angles. So let's start with the first one we have here, phi s equaling 19.3 degrees. Well, let's act from our positive x, and let's move up by 19.3 degrees. And we can draw a line. Let's go ahead and switch the color here. Where this line is the distance from sigma x to an angle of 19.3 degrees. Oh, let's get this font size under control, right? And then we can repeat this for our other angle, phi s 109.3 degrees. We're starting from our positive x. We will find another angle, right? And when we look closely, we actually end up forming a right coordinate system between those two angles, right? So there's plus or minus 90 degrees between the 19.3 degrees and 109.3 degrees, right? Naturally. So this is great. So now we have a coordinate system and we can build our element. So let's do that. Let's build our element here. Oh, hold on. Let's put the block feature on here, here, and here. There we go. So now we've got our little element here, right? And our normal and each of these vectors is normal to our surfaces. So now that we have that, let's go ahead and then draw in the things that we know. So for our first phi here, the 19.3, we find our tau is equal to negative 64 megapascal. Well, we know that the negative value, about 70 here, that the negative sense tells us clockwise, right? Causing a clockwise sense of rotation. So for our element, if we draw our arrow going downwards, it's going to cause a clockwise sense of rotation. So we've got a negative 64 drawn on our body. And from that knowledge, from this going downwards, we know to maintain equilibrium, our other side must go up. And if we want to eliminate any sense of rotation, We need a couple moment that is opposite. And so now we're able to build our shear stress, the shape that they will produce. And we can note that all of these are 64 megapascal, right? Which is cool, which is great. So just knowing that one, finding this, knowing this is negative, it's going to cause a clockwise sense. We're able to build this entire element. And now the last but not least thing that we need to do is we need to put our normal stress. Remembering that at both angles, the normal stress is equal to 40 megapascal. So the normals on this element are all 40 megapascal. And so now we've drawn our extreme value shear stress element using the knowledge that we have, our basic knowledge here. And so for part B, we need to define the values of the shear stress, their directions, and draw our stress element. And we've done everything we needed to do. Okay. So now there's one more part to this problem. And, this part is going to take a bit of time. It's going to take a bit of time for us to build out. And that is for us to, part C, draw Mohr's circle for this problem. So we're going to do this step by step, building everything in until we get this Mohr circle done. So let's start. Let's start with assuming that we don't know much about this problem. Let's assume that we don't know the principal stresses yet. We don't know our extreme values of shear stress. Let's assume that we were being asked to draw a Mohr circle and we hadn't completed part A and part B. So what would we want to do? Well, we can start with 2 points of interest, the sigma 1 and sigma 2, or we can start with the approach of finding the center of the circle and finding its radius. Either one of those approaches is going to work well. For me, I always like to find those principles first. So let's go with that. Sigma 1 and sigma 1 and 2 is equal to sigma x plus sigma y divided by 2 plus or minus square root of sigma x minus sigma y divided by 2 squared plus tau xy squared, right? So if we take the original state of stress and plug it in there, we can find sigma 1 and sigma 2 as 104 and negative 24 megapascal, right, approximately. Okay, and then let's find our other two terms, tau 1 and tau 2, which are simply this second component. So let's just do that, tau 1 and tau 2. So those are equal to 64 and negative 64 megapascal. Now the cool thing is that that the extreme values of shear, the magnitude of those is equal to what our radius is, the magnitude of those. And then our C, the center, is equal to the average stress, so the first term, on a zero value of shear, right? So directly from our principal stresses and our extreme value shears, we can find the radius, we can find the center of our Mohr circle. So let's get started with the Mohr circle. Let's draw our coordinates. And let's tell ourselves, or let's remind ourselves, that the x-axis is positive normal stress, and that below the y-axis is positive shear stress, meaning counterclockwise, right? And above here is what we consider clockwise, right? Now, once we've done that, let's go ahead and put our points of interest. Let's start with the principal stresses. Sigma 1, that is 104 megapascal. Sigma 2 is negative 24 megapascal. Our center C is equal to 40 megapascal. All right? And let's go ahead and put the zeros there so we remember, where we're acting here. We're acting on the 0 y, right? And then what else do we know? We know that tau 1 and tau 2, those act with an average with the average stress, right? We know that a negative shear value is clockwise. So we can say 40 here, and our negative 64, we could just put it 64. And here is 40, 64. So we don't have to put the cents in there if we don't want to. Or we can. In fact, why not? Let's put the cents in here, just to be consistent. Negative 64 here, right? So now we got our 5 points of interest, and maybe I need to move these up a little bit so we can get a nice looking circle. But let's go ahead and draw our circle now. Let's make it green, shape feature, and see if we can get a nice circle. Not too bad. We just need to make it more circular and move some of these points over. So that they all fit where they should be. And let's clean this one up here. So now we've got more circle here. We've got the circle drawn, and we've got our points of interest. Now the only thing that we're missing, the last thing that we're missing, is the line that represents our positive x-axis and our y-axis, right? So we need to find those points of interest wherever they are. They could be here, they could be there. We need to draw that line that represents the positive x-axis. So how do we do it? How do we define it? Well, let's start with what our original state of stress is. We have sigma x being 80, sigma y being 0, and tau xy is equal to 50 clockwise, or we can just say negative 50, right? So let's look. If the sigma is 80, sigma x is 80, then we should be somewhere over here. And if tau xy is equal to negative 50 or 50 clockwise, we should be somewhere up here. So this point, say this point should be 80, representing the sigma x, and the negative 50, representing the tau xy. And on our opposite end, if we were to trace this line through our center, we're going to find our other point of interest, where sigma y happens. Sigma y is equal to 0. And look, we're right on that 0, right? So 0. And the opposite of this tau on the other side would be positive 50. So 50 clockwise, so just positive 50 here, right? And then with that knowledge, we can go ahead and draw our nice smooth line here. want you to link. Let me just draw it a little bit longer than it needs to be. And of course, I'm not a perfect artist here, so let's just move this over a little bit. There we go. So now we have the line that represents the axes, the original axes through this Mohr circle. And let's note that this is the positive x side, meaning that we have sigma x and tau xy, and this is the positive y of the body. So we have 0 and we have the positive 50 on this side. And so we've been able to draw our Mohr circle. All right? Now the last thing with Mohr circle is the angle, finding the angles. Right? And we know that when we're performing our rotation, when we're rotating by phi, that we're going from the positive x-axis and we're rotating by a certain amount, right? So if we start at our positive x-axis and we wanted to rotate to our principal, well, then we can find an angle of phi p. I think it's 2 phi p. An angle here, 2 phi p, which represents the angle between the positive x-axis and the first principal direction, right? Which is great. And so we've drawn and properly labeled our Mohr circle. And note that every one of these points that's labeled. Each of these points is important. So like on an exam, if you were asked to draw a Mohr circle, you need to be able to label properly every one of these points in this diagram. Now we got a little bit more to do, and we'll be finished with this problem, and that is a part D here. Part D, which is find the principal directions using Mohr's circle. So if we just have Mohr's circle, right, and we don't have our tan equation, and we don't have that equation, what would be the way for us to actually find that principal value? Well, let's look at Mohr's circle here. We know that the angle between the positive x-axis and the principal direction is 2 phi p, right? And if we're going from positive x to this point, so we're rotating from here to there, let's make it easier and say, hey, from here to here, right? 2 phi p. Well, that would be 2 phi p1 because we're approaching sigma 1, right? Similarly, if we go the opposite direction and we rotate from here to here, well, we would then be approaching sigma 2, right? So we would have phi p2. So for each of these, we can very easily understand what angle we're finding by what value of stress we are approaching, right? But in addition to that, Mohr's circle, if we look at it, it's all geometry. We can use this geometry to try to figure out what is this angle 2 phi p. So let's take this. Let's take this little this section here, this sliver, this pie cut, and find the angle. Well, our little pie here has one side from the center to so this line here, right? From the center to the positive x-axis, and then we can draw a line straight down and a line over to give ourselves a right triangle. And that right triangle, using trig, we can actually find the angle of 2 phi p. So let's do that. Let's form this right triangle where this side is equal to r, right? It's from the center to the surface of the circle, so it's equal to the radius, and r is equal to, we can go ahead and just say R is equal to 64, right? And then if we go up here, if we start from 0 and we move upwards to the point on this surface, we're going to be at what? We're going to be at 50, right? And in fact, we will be at negative 50. And then if we move from the center over to this point, then we have 40. Right? And then we can draw our little angle in here, 2 feet P. And when we use trig, we'll find that same relationship that we originally started with. We'll find that same relationship where the 2 feet P is equal to the tan inverse of negative 50 over 40. Let's put the negative sign there, which is equal to negative 51.3, such that our phi P is equal to negative 20. It's negative 25.7 degrees, and that is associated with our phi P1, right? So we've actually proven that hey, using a little trick here, we can find the phi P1. And then if we have this knowledge, then we can go on and just using Mohr's circle, we can even create our stress elements, right? So just using this knowledge here, just using Mohr's circle, we can create our principal stress elements, and then we could also repeat this process and find our shear stress elements by remembering a certain relationship. Remembering that phi S is equal to phi P plus or minus 45 degrees. Remembering that from our previous lecture, from the previous lecture video, right? So, by using Mohr's circle, we can graphically solve for a lot of the things that we would do, that we would need to use the full principal stress and extreme value shear stress equations for. Now, in your homework, as well as on the exams, you'll be asked to do any of these methods. You'll be asked to do A, B, C, or D. So it's very important for you to get a lot of practice with solving these problems. And so we're going to see a lot of these in our homework, and we're going to continue to use the principal stress equations to look at how do we then predict static failures in parts that are subject to multi-axial states of stress, where there's a lot of different stresses going on. Can we use principal stresses or shear stresses, the extreme values, to tell us the onset of fracture in parts? So that's the end of this lecture 4. There should be some homework that I'll assign shortly for you to get some practice. And our next lecture will go into the ideas of elastic strains, thermal strains and stresses, and uniform stress. And then after that, we will have our first exam. So thank you for taking the time watching this video. Hopefully you've learned how to apply Mohr's circle, and that's it.